All right, now we're ready to finish up this problem and show that we can get solutions for the finite well. We can find the energy of the quantized states. All right, one moment. All right, this is what we've shown so far. For this problem, the finite well, we found that if we search for even parity solutions, we can find them. The solutions look like a decaying exponential outside of the well, and they look like a cosine function inside of the well. And they have to satisfy this equation, that the tangent of KL over 2 is equal to alpha over K, where K is known. It's square root of 2me over h bar. So it's just determined by the energy of the state. And alpha is determined by this equation, square root of 2m u0 minus e divided by h bar. And we recognize that both of these functions, terms, k and alpha, are both uniquely determined by the energy. Okay? And then the last thing we have to do is figure out, how do we solve this equation? How do we find the magic value of the energy, which will solve this complicated looking equation here? Okay? Now, this type of equation can't be solved analytically, but it can be solved numerically, and that's what I want to show you. Here, 1 second. We've switched to PowerPoint here, and there we are. Here's what we can do. We have this equation we need to solve. We can simply graph the right-hand side of the equation and the left-hand side of the equation separately on the same graph. Each of these is a function that depends only on the energy. So we'll make a graph of the function as a function of the energy. So for example, this black curve here is alpha divided by K as a function of energy. And now I'll just plot on top of that tangent of KL over 2. And any time that those two functions cross, that represents a solution. Now in this case, I can only do this if I know what the values of L and U naught and M are. Okay, so I can only find the solutions, the energies, for specific cases. All right, I don't get a general formula for the solution, but I can solve it for these specific cases. Okay. There we are. So here is tangent of KL over 2 plotted. Actually, this is just part of this. Remember that the tangent function blows up at certain points. This is the first point where it blows up, and goes to positive infinity here, negative infinity there, and then I've just continued it here. Can you see that this function has two places where it intersects the black curve? This one at an energy of about, I don't know, 6 or 7 electron volts, and this one at an energy of about 45 or 46 electron volts, okay? So those are the energy of two bound states. The first one is the ground state, the lowest bound state, because, okay? And the other one is an excited state. Now, the lowest state is, the lower state is probably the ground state, because we expect that the ground state will have even symmetry based on those sketches we made back at the beginning of the problem. Sorry. This case is also an even symmetry solution, okay? But we probably expect there to be an odd parity solution in between them, okay? But again, based on our sketch from before. Because if these wave functions look like the particle in an infinite well case, then we know that the first one looks a lot like a cosine function. Then there'd be a solution that looks a lot like a sine function, and so on. All right. Now I'm going to leave it for an in-class problem to show that the odd parity solutions have to satisfy this equation, minus cotangent KL over 2 is equal to alpha over K. But once we know that, we can simply graph the left-hand side of the equation, that's what's shown in red, and look for intersections between the left-hand side of the equation and the right-hand side of the equation, shown in black. And we see one here at about 21 electron volts. And so now we found the three bound states of this system, okay, which are at 5.71 eV above the bottom of the well, 22.15 EV, and 45.34 EV. And actually, those are the only bound states for this system. There are no other bound states at higher energy. We've exhausted them all. All right, well, let's stop this problem here, okay? It's a difficult problem. It had a lot of steps. I really wanted to show you how it works, just so you can see how problems like this can be solved. How did we do it? We took our potential, we divided it up into regions. Here, actually, I'm going to stop sharing. We took our potential and we divided it up into regions. Within each region, we could find the solution to Schrodinger's equation, and then we simply matched up the solutions at the boundaries between them, okay? This technique can be generalized, and it even can be automated, so that at least in one dimension, we can break up any problem in the way that we've broken up this one, and then solve it with a computer. And you'll look at some computer simulations like this in class and on homework as well. Anyway, I wanted to show you that. So, but again, although this is a very complicated problem, which is maybe a little scary, this is also the most complicated problem that we're going to do in this course. All right. See you in a bit.